Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 28, Phi Networks and Protocol Stack, the Reality Internet. Remember the language we are learning. There is one field, Phi, the Holophase, one continuous cyclic movement from which all of reality unfolds. When Phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We stand at the precipice of a new horizon in Book 10.5, Information Systems. We have built the pieces, the communicators, the memories, the computers. Now, we weave them together. We enter the network nexus. Holographic displays here don't show individual systems, but topologies of light and data, a living, breathing map of countless phi nodes. Foundries in Berlin, sensor arrays in the Pacific, memory vaults in orbit, computational engines beneath mountains. Lines of shimmering connection pulse between them, carrying not just packets, but synchronized phase references, coordinated field patterns, distributed coherent states. This is not the Internet of Information. This is the reality Internet, a network for sharing and co-creating coherent states of the physical world itself. Your new skill is that of the network architect. You are learning to design the protocols, the rules of handshake, consensus, and trust that allow distributed phi systems to act as one coherent mind, one coordinated hand. Scene: the network nexus. The room is a sphere of light. Projected in its center is a real-time model of the global phi network. You see clusters, clouds of coherence, where many nodes share a tightly synchronized phase reference, pulsing like fireflies in unison. Between clusters, thicker trunks carry aggregated data streams, but also calibration signals and constraint updates that keep the entire web aligned to the HLS standard. Alarms blink softly at the edge of your awareness, a latency spike on a transatlantic phi link, a minor phase drift in a lunar sensor cluster. Self-healing protocols are already engaging, rerouting, resynchronizing. On your console, you drill down. You see the protocol stack for a simple transaction. A foundry in Tokyo requests a specific topological defect pattern from a memory library in Geneva. The stack unfolds from the high-level application request down through layers that handle routing, reliable delivery, link management, and finally to the physical modulation of a laser beam or microwave carrying the phi pattern itself. Our puzzle is one of scaled coherence. How do we design a layered set of protocols that enables thousands, millions of heterogeneous phi systems to communicate reliably, to agree on shared states, like a global phase reference or a sensor reading, and to coordinate complex actions, all while maintaining local coherence and resisting failure or attack? We are moving from building telephones to building a global nervous system. The language role, the coordination and scaling skill. This part teaches us systems integration skill. It is the skill of designing layered abstractions that manage the complexity of distributed phi systems, allowing them to achieve shared goals, consensus, and exchange meaningful patterns, communication, without requiring every node to understand the full global state. Our core question about phi is, given a population of distributed phi systems with local constraints and noisy channels between them, what set of message passing and adjustment rules will allow them to converge to and maintain a consistent view of shared phi state information and to reliably transport arbitrary phi patterns from one point to another in the network? We are moving from speaking in sentences to orchestrating a global conversation in the language of phi. The anchor image, the symphony orchestra without a single conductor. We will use the anchor image of a large, distributed orchestra without a single central conductor. Each section, strings, woodwinds, brass, has its own lead player. They must start together, stay in time, and follow the same score. How? They listen to each other. They might all tune to the same reference note from the oboe. They watch each other's breathing and bowing for cues. They have local protocols. The first violinist nods to the cellos to begin. The trumpets watch the conductor's baton on a screen if they're in another room. The global coherence of the symphony emerges from local interactions and shared reference signals. Our network protocols are the rules for that listening, nodding, and screen watching at a planetary scale. The coherence selection principle in networking. In a network, coherence is emergent synchronization and agreement. Constructive resonance, alignment in networking means nodes achieve consensus on shared data or phase. Links maintain synchronization. The network as a whole settles into stable, predictable states. It is a coherent entity. Destructive resonance, dissonance means network partitions, where one group of nodes believes one state, another group believes another. Feedback oscillations in routing or consensus algorithms. Incoherent noise, overwhelming signals. The network is schizophrenic, unstable, useless. The network architect's mantra is about preserving global harmony. If coherence breaks, we stop. If coherence returns, we continue. If a partition is detected, consensus becomes impossible between subgroups, the network isolates the partition, prevents inconsistent operations, and attempts to heal. It does not allow two contradictory realities to be acted upon. Core mechanisms: the Phi protocol stack and consensus. We build our network in layers, each solving a specific problem. The Phi protocol stack, a layered reality. Inspired by TCP/IP, but rebuilt for Phi. Physical layer, the raw Phi channel. This is the foundry hardware, the laser link, the acoustic transducer. Its job is to send and receive symbols modulated in Phi, phase, OAM, topological charge. This is where 10.5.1 lives. Link layer manages direct node-to-node connections. It handles framing, packaging bits into Phi symbol frames. Error detection, using Phi parity checks like verifying topological charge integrity, and medium access control. Who gets to talk on a shared channel? It ensures a coherent pipe between neighbors. Network layer, the routing layer. It uses addressing to move Phi packets across multiple hops. It must find paths that respect coherence budgets, low latency for phase-sensitive traffic, high bandwidth for pattern transfers. It's the post office of the reality internet. Transport layer ensures reliable end-to-end delivery. It might implement a FATTCP, a protocol that acknowledges receipt and retransmits lost packets. For real-time fast streaming, like a shared sensor feed, it might use a lighter weight, unreliable, but timely protocol. Application layer, the user-facing layer. Protocols here include fast state sync protocol for sharing phase references, pattern transfer protocol for moving defect designs, consensus protocol for agreeing on sensor readings or actions, 2-point, fast state consensus algorithms, agreeing on reality. This is the most critical new protocol. When multiple nodes measure the same Fa field, for example, a gravitational wave passing by, how do they agree on its phase and amplitude? Phase locking loops across networks. Nodes exchange their local phase estimates. Each node adjusts its own estimate slightly toward a weighted average of its neighbor's estimates. This is a distributed, coupled oscillator problem. With good network connectivity, all nodes converge to a common phase. This is consensus by synchronization. Byzantine fault-tolerant BFT consensus. Some nodes might be faulty or malicious, sending false data. We need protocols that can agree on a value even if up to 1/3 of the nodes are lying. This borrows from blockchain, but is optimized for physical state verification. A node's vote can be weighted by its reputation score, historical accuracy, or by the physical impossibility of its claim. For example, reporting a phase value that would violate known channel constraints. 3. Gateways to legacy systems. The reality internet must talk to the old internet. Gateways translate between TCP/IP packets and Phi protocol messages. They also act as coherence buffers, converting between discrete lossy packet data and the continuous phase-sensitive streams of the Phi world. The coherence criterion: global phase coherence or stable relationship. Our coherence criterion for the network is specific. The network must maintain global phase coherence or a stable phase relationship where required for distributed applications. For a distributed sensor array forming a giant telescope, this means all nodes must share a precise common phase reference to within a fraction of a wavelength. For a distributed computing cluster, it might mean synchronized clocks to coordinate steps. For a social network of shared experiences, it might mean agreeing on the sequence of events, a logical, not physical phase. Where absolute phase isn't needed, the criterion relaxes to consistent state consensus. Everyone agrees on the facts, even if their local clocks aren't nanoseconds synchronized. The dissonance indicator, partitions and oscillations. The primary dissonance indicators are network partitions and feedback oscillations. Network partitions, a physical or logical split that prevents subgroups of nodes from communicating. This leads to inconsistent phi states. One partition thinks the field is in state A, another thinks B. If both act on their belief, they create contradictory physical interventions, the ultimate network failure. Feedback oscillations. In routing or consensus algorithms, a configuration error can cause state updates to bounce back and forth, amplifying. For example, nodes overcorrecting phase estimates based on each other's corrections, leading to growing phase swings instead of convergence. The network becomes an unstable, screeching feedback loop. Detecting these is paramount. They signal that the network's coherence is broken. The safety rail, Byzantine fault tolerance and graceful degradation. Our safety rail is about survival under failure and attack. 1. Byzantine fault tolerance, BFT. Network protocols, especially consensus protocols, must be BFT. They must be designed assuming that some nodes will be malicious, Byzantine, and will lie, delay, or send conflicting messages to disrupt the network. A network that can be crashed by one malicious node is not safe for reality engineering. 2. Graceful degradation. The network must not suffer catastrophic collapse under partial failure. If a major backbone link fails, traffic should reroute, perhaps with reduced bandwidth or increased latency, but the network should keep functioning. Services should have fallback modes. A distributed computation might slow down, not stop entirely. The safety rail rule. No network protocol is deployed without passing stress tests that include simulated Byzantine nodes and multiple simultaneous link failures. The network must fail softly, not shatter. A measurement scene, the three-node phase consensus. Let's enact our roadmap's measurement scene. Scene, a network of three optical sensor nodes on three mountain peaks, trying to agree on the phase of an incoming laser wavefront from a satellite, despite atmospheric turbulence causing different phase shifts at each node. Goal, converge to a common, accurate phase estimate. The protocol, a simple distributed phase locking loop. Each node measures the phase locally, noisy. They broadcast their measurement to the others. Each node then computes a weighted average of all three measurements, including its own, and adjusts its local phase reference towards that average. They repeat. The pass coherent consensus. 1. Nodes start with different noisy phases. 2. They exchange messages over a reliable link layer. 3. Within 10 iterations, milliseconds, their phase estimates converge to within 0.1 radians of each other. 4. A trusted central observer, for example the satellite itself or a fourth ultra-stable reference, confirms that the consensus phase is within the expected error of the true incoming wavefront phase. FAS. The network achieved coherent consensus quickly and accurately. The fail, incoherence or instability. Fail and non-convergence. The estimates never settle. They drift or remain far apart. The protocol is unstable for the given noise level or latency. Fail B, Byzantine failure. One node is malicious and sends random shifting phase numbers. The other two nodes, running a naive averaging protocol, are led astray. Their consensus is wrong and unstable. Fail C, oscillation. The estimates oscillate with growing amplitude, a feedback loop. The network is incoherent and noisy. Fail. The protocol is inadequate. It must be redesigned with better filtering, BFT features, or damping. The prediction spine, the hallmarks of a scalable phi network. A well-designed phi network yields a clear prediction spine. 1. Scalable overhead. The network will allow the number of nodes, n, to scale without requiring per-node resources, bandwidth, memory, state, to grow faster than of log n. This is the key to internet-scale growth. A protocol requiring every node to know every other node, of n square, is doomed. 2. Efficient physical consensus. Phi-state consensus for physical measurements will be reachable faster and with less overhead than blockchain-style proof-of-work consensus. Why? Because the consensus is about physical truth that can be partially validated locally. Does this sensor reading make physical sense? And because the coupling is often natural, phase signals from the same source. The prediction is that the convergence time will be dominated by network latency, not by artificial puzzle solving. 3. Graceful degradation. Under link or node failures, the network's performance, throughput, consensus accuracy will degrade smoothly and predictably, not drop off a cliff. The measure of a robust network is not that it never fails, but that it fails in a way we can manage and repair. Falsifiability, when the network cannot hold. Our falsifiability threads test the very possibility of a global reality internet. Falsifier 1, the impossible consensus. If network consensus on physical phi states cannot be achieved in the presence of realistic noise, latency, and a small fraction of faulty malicious nodes, then distributed phi engineering is impossible. We could never coordinate multiple foundries to work on a single large-scale pattern. Each would be an island. This would be a profound limit on collaborative reality shaping. If the overhead of maintaining network coherence, the bandwidth for sync messages, the computation for consensus, the energy for constant correction, consumes all the gains obtained from distributed processing or sensing, then the network is pointless. It's a beautiful, self-consuming artifact. The network must provide a net utility. These falsifiers keep our ambitions grounded. Can we really build a nervous system for the planet, or are we doomed to a world of isolated, chattering organs? Tri-unity in networking. A network is a magnificent triune entity. Time echo, synchronization, and latency. The rhythm of the network, the clock synchronization, the heartbeat of hello messages, the propagation delays, latency. This is the network's temporal fabric. The layout of nodes and links, the physical and logical connections. This is the network's spatial map. It defines which nodes can talk directly and which need relays. Motion echo, the movement of packets and the evolution of consensus states across the network. This is the network's dynamic life, the purpose of its existence. Designing a network means carefully engineering all three, minimizing latency time, optimizing connectivity space, and ensuring robust, efficient flow and agreement, motion. Lanterns across scales, the protocol of everything. The need for coordination protocols arises wherever independent agents share a goal. Near scale, cellular signaling networks. Cells in your body use chemical and electrical signaling, a biochemical phi network, to coordinate growth, immune response, and metabolism. The protocols are evolved molecular pathways. Failure leads to disease, cancer, a cell ignoring consensus signals. Middle scale, air traffic control. A global network of aircraft, ground radar, and control centers. Protocols define communication frequencies, handoff procedures, and collision avoidance rules. The consensus is a shared, accurate map of who is where. A partition, loss of radar, triggers safety protocols, holding patterns. Interplanetary internet with minutes or hours of latency, traditional TCP breaks. New protocol, bundle protocol, are designed for asynchronous, store and forward operation. This is a precursor to a true Phi network spanning the solar system, where phase coherence at such distances is impossible, but state consensus agreeing on a spacecraft's collisions is vital. Hung, the ethics of the reality internet. Trust in the substrate. The ethics of the Phi network is the ethics of the Phi network, the shared truth and secure foundation. Of course, 1. Truthful consensus as a public good. The network's ability to reach consensus on physical facts, for example, the atmospheric CO2 phase is X, becomes a public utility. Manipulating this consensus via Sybil attacks, overpowering transmitters, is an attack on shared reality. The ethical duty is to design uncorruptible protocols and to openly audit the consensus process. 2. Access and equity. The reality internet could create a new divide. Those with access to high coherence, low latency links, and those without. The network protocol design should encourage decentralization and interoperability to prevent monopolistic control over the substrate of shared reality. 3. Containment of failure. A bug in a widely deployed Phi protocol could cause synchronized failures, many systems acting on a false consensus. The ethical design includes circuit breakers, versioning, and the ability to segment the network to contain protocol failures. The power to network reality brings the duty to make that network truthful, accessible, and safe. The most reliable thing we have ever built. The recognition skill, seeing the protocol in the wild. You know you need the skill when you see a system of independent actors coordinating without central command, and you ask, what are the rules? How do they agree? A flock of birds turning in unison, local alignment rules. The stock market settling on a price, a kind of consensus via bids and asks. The immune system mounting a coordinated response. Wikipedia editors converging on an article, a slow, human-mediated consensus protocol. The moment you dissect the process of agreement and coordination, you are thinking like a network architect. The next step is to formalize those rules and make them robust enough for machines that shape reality. The master tree location. This part, 10.5.4, is the capstone of synthesis for book 10.5. It depends on 10.5.1 for the physical links, on 10.3.3 for managing node resources, and looks ahead to 10.7.2 for the societal analogs. It is the glue that binds all information systems together. It enables the final piece, AI Co-Engineer 10.5.5, which will use this network to learn from and collaborate with countless other systems. It is the prerequisite for the societal transformation, book 10.7, that a reality internet makes possible. This is the infrastructure for a coherent civilization. Return to the phi. Let us zoom out. The phi network is a meta-phi structure, a pattern of communication and agreement overlaid upon the physical phi fields of its constituent nodes. The protocols are strain clauses for information flow and agreement. They create a higher-order coherence, the coherence of shared knowledge and coordinated action across space and time. The single field, phi, manifests as light in fibers, as sound in air, as voltage in wires, and as agreement in protocols. The network is the field learning to know itself, to reflect upon itself, and to act upon itself in a coordinated manner. We are building the mirror in which the universe can see its own coherence and choose to enhance it. Zenodo and the equations of the handshake. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers detail the stability analysis of distributed phase locking algorithms, the design and proof of Byzantine fault-tolerant consensus protocols for physical systems, the information theoretic capacity of networks with coherence constraints, and large-scale simulations of phi network performance under stress. They provide the rigorous foundation that turns the vision of a reality internet into a buildable, testable global infrastructure. So, picture yourself back in the network nexus. The global hologram pulses with healthy, coherent light. A request from a research team in Cape Town for a complex material simulation has been routed automatically to a distributed computational cluster spanning 5 foundries. The phase references are synchronized, the work is divided, the results are consensus verified and streamed back. All this happened in seconds without a human touching a router table. You have just witnessed the reality internet in action. You have learned the principles of its protocols, the rules that allow a planet of phi systems to think and act as one. This is part 10.5.4, Phi Networks and Protocol Stack, the Reality Internet. It is the connective tissue of Book 10.5, the foundation for everything that follows. In our final part of Book 10.5, we will introduce the ultimate user and partner of this network, the AI Co-Engineer, 10.5.5. We will learn to design artificial intelligences that don't just process data, but that learn the grammar of phi from the network itself, that propose new designs, debug foundry operations, and collaborate with human engineers as fluent co-authors of reality. We will learn to build the mind that will live in and tend to the nervous system we have just designed. Remember, one field, phi, with its infinite echoes. We have built the threads that connect its echoes across the world. Now we will create the weaver. Salam and peace be upon you.